Hello everyone. Previously we have tried to discuss about vectors. We have defined what vectors are. We have also tried to see about the different types of vectors. And at last we have also tried to see about how to operate with vectors. We have also seen that vector can be added or subtracted using geometrical and analytical means. The other thing that we have seen is about vector multiplication. We have seen about the cross product and the dot product of vectors. The sum or difference of two vectors always result in vectors, but the product of vectors might give us scalar or vector, depending on the type of the product. The dot product results in scalar, so that it is called scalar product. The cross product of two vectors result in vector, that's why it's called vector product. And the other thing that we have seen is the applications of vector. Some of the common applications of vector have been studied previously, and these are the scalar projection, the orthogonality of vector, whether two vectors are perpendicular or not, the collinearity of vector, whether two vectors are parallel or not. We have also tried to see about how to determine the area of a parallelogram using a cross product, and the volume of a parallelepiped using a triple scalar product. This was what we have seen previously. And today we'll try to discuss about the most important point about kinematics. Kinematics, we'll try to see about the one-dimensional motion and two-dimensional motions. So on this unit, we'll try to define what motion is, and we'll try to see the different types of motion depending on the acceleration. We'll try to categorize this motion as uniformly accelerated motion, and accelerating motion. We'll try to use the four most important equations and apply on some problems. We'll try to define what projectile motion and circular motion are. We'll try to see them under two-dimensional motion. So let's proceed on that. First, let's try to define what kinematics is. Kinematics is a branch of physics which studies about motion and motion variables, but not the cause. The cause of motion is force. We are not investigating here about force. We only focus on motion and motion variables. So what is motion? First, we should have to define what motion is. Motion is the change of position of something with respect to a frame of reference. A frame of reference is something which is very important to designate the location of other objects. Therefore, motion is a change of position relative to a frame of reference. And whenever we are trying to discuss about motion, there are motion variables or parameters, very important motion parameters. And these are position and displacement. Position is sometimes also known to be distance, or usually we call it to be distance. Distance and displacement are the two important parameters or variables. The other variables are speed and velocity. We'll try to see about that, and we'll try to see about acceleration. Position is both position and displacement, or distance and displacement are lengths. They are lengths. but their difference is that distance, it measures the total path length between 2 points. It measures the total path length between 2 points. It is a scalar quantity. Whereas displacement measures the shortest path length between the 2 points. And it's a vector quantity. It's a vector quantity. Suppose here we have a particle that it goes with 4 meters to the east. Might move 4 meters to the east. And it might move 3 meters to the north. We can take these two. Whenever we are trying to determine distance, we should have to add all the distance. All the length between the two is the total path length. So therefore, 4 meters plus and 3 meters gives us 7 meters. 7 meters is the distance between the 2 points. But if you are asked to find the displacement, it should be the shortest path length between the 2 points. That means we should have to construct like this. The distance between the shortest path length between the 2 points gives us, using Pythagoras theorem, it gives us 5 meters. So 5 meters is the displacement, whereas 7 meters is the distance. Therefore, distance and displacement are the two important parameters. The difference between them is one is to locate the total path length, the other is the shortest path length. And the other parameters is speed and velocity. Speed measures, it is a ratio of distance to that of time. Because we have said that distance and displacement has a difference. This one is scalar quantity, this is a vector quantity. The same is true for speed and velocity. Speed is a ratio of distance covered per unit time t. Whereas velocity is the ratio of displacement per unit time t. It's a ratio of displacement per unit time t. Both are measured using meter per second. Here, both are measured using meter. For speed and velocity, both are measured using meter per second. Now let's try to see the different types of velocity. It's possible to discuss about average and instantaneous velocity. Average velocity is a velocity between two given time intervals, whereas instantaneous velocity is a velocity at a given instant time. At a given instant time. Therefore, suppose here, let's try to discuss about, let's try to give a displacement, and that displacement is dependent on time t. Let's say that x, or you can say that s, that is displacement, as a function of time t, 2t squared plus 4 using meter. Let's say that this is the displacement as a function of time t. So, as time varies, the displacement of the moving object or the particle also varies or changes. In this case, if you are asked to find the average velocity between two time intervals, let's say between time t1 is 1 second and time t2 be 2 seconds. What is average velocity between the 2 seconds? That might be the question. So to find the average velocity, you should have to find the displacement at the two different time intervals. Therefore, what is the displacement at time t 2 seconds? It's possible it's possible to add these two here, and 2 squared gives you 4. 4 times 2, 8. 8 plus 4 gives us 12 meters. The correspondent displacement, or the displacement of the particle at time t2 is 12 meters. The particle reaches at 12 meters at time t2 second. How about at time t 1 second? When you put 1 here, 1 squared gives you 1. 1 times 2 plus 4 gives us 6. Therefore, the correspondent displacement gives us 6 meters. 6 meters. Therefore, the average velocity between the two time intervals gives us, the average velocity gives us the x2, the displacement at time t2 minus x1 over time t2 minus t1. This is what or how we determine the average velocity. Therefore, when you add 12 here, when you put 12 here, minus 6 over the time t2 is 2 seconds minus 1. When you subtract this, gives you 6 over 1. Therefore, the average velocity becomes 6 meters per second. This is how we determine the average velocity between two time intervals. Whenever we are trying to discuss about instantaneous velocity, Instantaneous velocity is a velocity we are asked at a given instant time. At a given instant time. Suppose for the question provided above, here we have a particle moving with this function, the displacement which depends with time t. Therefore, it's possible to find the instantaneous velocity, like what is the instantaneous velocity of the particle at 3 seconds. At 3 seconds. Therefore, to find the instantaneous velocity, we should have to use a mathematical approach known as limit or derivative. Actually, you have learned this in your mathematics lesson. So it's possible to use the derivative techniques or the limit techniques. Therefore, it's possible to derive these functions and find the instantaneous velocity. How do we derive? Well, it's a mathematical approach. We should have to use derivative. We should have to put these two here. To v is equals to the derivative of displacement by dt. It's possible to find this like this. 2 brought here. 2, then brought the power of 2 to the coefficient. Then t, you should have to subtract 1 from the power, plus 4 has no power, means to the power of 0. Whenever you put 0 here, 4 into 0 gives us 4. Whenever you derive constant numbers with respect to time, is 0. Therefore, this gives us 4 times t. 4 times t is the velocity with respect to time. Then we have asked to find the instantaneous velocity at a given instant time. Suppose the time is 3 seconds. Therefore, the velocity instantaneous at 3 seconds means we should have to put 4 and the time is 3 seconds. Therefore, this gives us 12 meter per second. 12 meter per second is the instantaneous velocity of this particle at, once again, at a single second, and that second is 3 seconds. Whenever you are asked to find average velocity, it should be the average velocity between 2 time intervals. So these are the 2 important terminologies. And the other point here is it's the same is true for acceleration. Acceleration also, we have average acceleration and instantaneous acceleration. To find the average acceleration, it's acceleration between 2 time intervals. The velocity function at time t2 minus velocity at time t1 over t2 minus t1 is average velocity. Whereas if you are asked to find instantaneous acceleration, it's acceleration at a given instant time t. Therefore, it's possible to use the derivative of velocity function. Now, let's try to see about types of motion. Depending on acceleration, we do have 3 types of motion. On a given rectilinear or motion along a straight line, we have 3 types of motion depending on acceleration. What are they? And these are uniform motion, uniformly accelerated motion, and accelerating motion. The parameter is acceleration. For a uniform motion, acceleration of that body is 0. We have 0 acceleration. That means the acceleration is 0 while the velocity remains constant. For a moving object, the velocity remains constant. Okay? The initial velocity of that particle is the same as the final velocity of that particle. Therefore, the motion is said to be uniform motion. Uniform motion has constant velocity. If the velocity is constant, the acceleration is 0. We know that we define acceleration as the final velocity minus the initial velocity over time t. But velocity initial and velocity final are equal. If you put these equal, if you subtract equal numbers, it will give you 0. Therefore, keep that for a uniform motion, acceleration is 0, but velocity remains constant. And here, for a uniformly accelerated motion, the acceleration remains constant. The acceleration remains constant. The rate of change of velocity remains constant, or the acceleration remains constant. One good example is free fall or vertical motion is a good example of uniformly accelerated motion. When an object is thrown downward or upward, we are using gravity, and gravity is always 9.8 or approximately for calculation 10 meters per second square. So the acceleration remains constant. The velocity changes, and that velocity changes per unit time t remains constant. Here the velocity remains constant, acceleration 0. But for a uniformly accelerated motion, acceleration is constant. Whereas accelerating motion is the motion in which the acceleration itself varies with time. Here the acceleration remains constant, and here the acceleration is 0, but for accelerating motion is a motion in which its acceleration itself changes with respect to time. So keep this in your mind, and we mainly focus on these two types of motions. We focus on uniform motion and uniformly accelerating motion. And the big four equations or mathematical formulas used for uniformly accelerated motions are this, and this it says for uniform horizontal motion, or it might be for a free fall vertical motion. For uniform horizontal motion, the big four equations can be given as the average velocity is equals to the initial velocity plus the final velocity over time t2. The final velocity is equals to the initial velocity plus acceleration time t, and remember that this acceleration is constant. And the final squared is equals to velocity initial squared plus twice of acceleration times displacement. And displacement s is equals to velocity initial t plus half times acceleration t squared. Look here, the acceleration remains constant. If you are trying to use this equation for a uniform motion, acceleration will be cancelled out here, here, and here as well. So for a uniform motion, you'll have, for a uniform motion, the only thing that you have is this equation. S is equals to velocity initial t. But velocity initial and velocity final are equal. In this case, velocity initial and velocity final are equal if it is for a uniform motion. For a uniform motion, the velocity remains constant, and the velocity average is the same as the initial, is the same as the final. Therefore, instead of using velocity initial or instead of using velocity final, it's possible to use velocity average. So displacement s is equals to velocity average times t. It's possible to use this one for a uniform motion. But usually use this equation, the big four equations, for a uniformly accelerated motion, and keep this in your mind. And for free fall, for objects thrown upward or downward, remember that you should have to convert the acceleration using gravity. For an objects which are thrown downward, you should have to use a plus sign here. And for objects which are thrown upward, you might use minus sign convention. And note that gravity is always positive 10 meters per second for calculation purpose, okay? So keep this in your mind. For a uniformly accelerated motion, we have to use these equations. It's also possible to represent motions using graphs. We do have a displacement velocity graph, velocity velocity graph. It's possible to have acceleration velocity graph, so we can have such a graphical representation. For a uniform motion, we have said that acceleration is 0. Acceleration 0, and the velocity remains constant. And the velocity displacement velocity graph, the slope shows us a velocity, and the slope remains constant. So note that, start from acceleration. For a uniform motion, acceleration is 0, so we have 0 acceleration. It is overlap on time t, on horizontal graph. So the acceleration remains 0 despite the change of time t. But here, it shows you velocity velocity graph, the acceleration is 0, but the velocity remains constant. At initial time, the velocity doesn't change. At some other time, the velocity doesn't change. It remains constant. Here as well, for displacement velocity graph, this shows you for a uniform motion. But for a uniformly accelerated motion, the acceleration starts from acceleration. The acceleration remains constant. Despite the change of time t, the acceleration remains constant. Suppose here if the acceleration is 4 meters per second squared, so at time t0, at time t1, at time t2, at some other time, the acceleration remains constant. Okay? But here, the acceleration is 0. When you come here, the velocity velocity graph, it shows you on this direction, the velocity changes. The velocity changes from 0 to 2, 3, 4, and the like. And the acceleration remains constant, meaning the time, the difference, the change of velocity between h and every interval remains constant. The acceleration remains constant, but the velocity increases. The same is true. Here we have a displacement s is equals to velocity initial t plus half at squared. We have a parabolic relation on displacement s. If the initial velocity is 0, you can put it here 0, 1 over 2 at squared. It shows you a parabolic relation. So this is true for a uniform motion, and this is true for a uniformly accelerating motion. Now let's try to see about motion in a plane or two-dimensional motion. So far we have tried to see about one-dimensional motion. Either the object is moving horizontally or the object is moving vertically. Both shows you one-dimensional motion. But in this case, we are trying to see a two-dimensional motion, meaning the object moves in both directions, or the object has both components, the horizontal and the vertical component. So two-dimensional motions consist both horizontal, meaning along the x-axis, and vertical along the y-axis. So in such motions, we have different quantities. Previously, we have seen the basic parameters, the displacement, the velocity, and the acceleration. All these components have the horizontal and vertical component. So displacement have the horizontal, vertical component, velocity as well, acceleration as well. So we'll try to see those things in motion in a plane or two-dimensional motion. The two important two-dimensional motions are projectile motion and circular motion. So first, let's try to see about projectile motion. Projectile motion. Suppose you project a given particle or a given object at an angle of theta from horizontal. So let's see here. Suppose you are trying to throw something upward from horizontal at an angle of theta. At an angle of theta. You just project it with an initial velocity v0. Then the object that is thrown is called projectile. Projectile. We call it to be projectile, and that projectile has a trajectory motion. Trajectory means which is represented by quadratic or parabolic, or it's possible to say semicircular pattern. So it has such a pattern. If you are throwing something, it will move like this and falls apart at some points there. Therefore, here you have the initial velocity. The initial velocity has horizontal and vertical component. At every point, it has horizontal and vertical components. The displacement as well has horizontal displacement and vertical displacement. When we are trying to discuss about acceleration, the acceleration along the horizontal component and the acceleration along the vertical component on a projectile motion is a constituent of two different types of motion. The horizontal projection tells us about uniform motion. Uniform motion. The horizontal projection or the horizontal component of a projectile motion is uniform motion. And previously we have said that uniform motion has zero acceleration. Therefore, the horizontal component acceleration is zero because that projectile motion is uniform motion. Projectile motion, the horizontal component of projectile motion is uniform motion. Uniform motion. Keep this in your mind. Okay? If the acceleration is zero, it's a uniform motion. If it is a uniform motion, the velocity remains constant. You have to keep this in your mind. But the vertical component of a projectile motion is uniformly accelerated motion. It is uniformly accelerating motion. So that the acceleration due to gravity is used instead of A along the y-axis. So we can use gravity. So we have the horizontal, the vertical component. To understand this concept, let's try to see at some points, some common points. Let's start with the initial point here, at some point here, and at the maximum height here, and finally, let's try to see at point 4. So when we are trying to see at point O, or at the original point, there is an initial velocity v0. The object is launched with an initial v0. And this v0 has horizontal and vertical component. The horizontal component, the initial velocity v0 along x. It's possible to say the initial velocity horizontal component, v0 x. And the horizontal component can be determined using your mathematical or trigonometric relation, sine and cosine relation. So if I use cosine theta means adjacent over hypotenuse. The hypotenuse is the initial velocity v0, and the adjacent is the horizontal component of this velocity, v0 x. So v0 x over v0, from this, the horizontal projection is known to be, or the horizontal component of the velocity is said to be v naught cosine of theta. This is how we determine the horizontal component of the initial velocity. And the vertical component of the initial velocity can be determined using sine. We know that sine is opposite over hypotenuse, therefore v naught y over v naught. And when you crisscross, you can find that the horizontal initial velocity component can be given as v naught sine theta. And one thing is the horizontal component and the vertical component. When you add these two, that means it's a vector quantity. You should not have to add linearly. Rather, you should have to use a parabolic condition, or you should have to use a trig condition. Therefore, the square root of v naught squared and vy squared under root gives you v naught, or the initial velocity. Suppose here you do have, let's take an example. The object is thrown with an initial velocity of 100 meter per second at an angle of theta be 53 degree. Suppose that the object is launched at an angle of 53 degree. Then what is the horizontal component of this velocity and the vertical component of this velocity? Well, to find the horizontal component, the initial velocity along x gives us, the initial velocity is 100 meter per second, and the cosine of 53. Cosine of 53 is given or known to be 0.6. So 0.6 times 100 gives us 60 meter per second. So 60 meter per second is the horizontal component of the initial velocity. Whereas the vertical component can be determined as v naught y, v naught sine theta. This is how we put. V naught is 100. The initial velocity is 100. And sine 53. Okay? Sine 53. Sine 53 gives us 0.8. 0.8 times 100 gives us 80 meter per second. Look here. 80 meter per second is initial vertical component, and 60 meter per second is initial velocity horizontal component. When you add these two, you are not going to add it linearly. Like 80 plus 60 is 140. This should not be the way, because it is 60 meter per second in the I direction, in the x direction. Previously we have learned about vectors, and this one is projected in the j component. It's moving in the j component. So what is the total velocity? You have to find the resultant velocity using this one. So 80 squared plus 60 squared should give us 100. This is how we determine the resultant vector. This is at the original point, or at the initial point. Now let's try to see what if the particle is moving and reach somewhere at point 1, at point 2, at different point t. Time t, it's possible to find the velocity v. We know that you do have 4 basic equations. Previously, we have said that it's possible to find the final velocity is equals to initial velocity plus acceleration times t. This is how we determine the final velocity. The final means it is a velocity after time t. Suppose you project the given particle at 100 meter per second. What will be the velocity after 2 seconds or 3 seconds, something like this. So to find the velocity v, you should have to have the horizontal and the vertical component. So you should have to use x and y, meaning the final velocity along horizontal x should be equals to the initial velocity along x plus acceleration along x t. This is the way how to find the horizontal projection after time t. And it's also possible to find the final velocity along y. The initial velocity along y plus acceleration along yt. Okay, we know this equation. The only thing we have done is along the x, along the y, the horizontal and the vertical projection. That's what we did. But we have said that there is no acceleration along the x-axis. There is no acceleration on the horizontal component of the projectile motion. So what does it tells is the initial velocity component. Previously we have found it to be 60 meter per second. We have said that we just launched it with 100 meter per second at an angle of 53. The horizontal component is found to be 60. So this 60 meter per second doesn't change despite the change of time t. At 1 second it is 60, remains there. At 2 seconds it remains 60. At any time t, the horizontal velocity remains constant. That's why it's called uniform motion. The horizontal component is called uniform motion, so that the velocity remains constant. But the vertical component depends on the vertical acceleration, and that is gravity. That's gravity. Therefore, suppose at point 1, what will be the final velocity? So to find this at point 1, here, at point 1, it's possible to find the velocity component among the big four equations. We have the v in y, means the vertical component along the y at some other time t. v naught sine theta minus g t. Here, we have said that v final y, or it's possible to use vy, the final velocity, meaning the velocity at a given time t. The initial velocity component, previously we have said that it is v naught sine theta. Sine theta. And plus here, we have to put the gravity. Gravity, acceleration along y is gravity, either plus or minus. We have a sign convention to use a plus sign when the projectile is moved downward, whereas minus sign when the projectile is launched upward. Therefore, this is launched upward. If it is launched upward, you have to use the negative g. But suppose on a given elevation, you might project something downward. Okay, you might throw something downward. At that moment, you can use plus sign. So plus or minus gt. Therefore, in this case, since we are launching upward, we should have to use the minus sign. The minus sign. This is a sign convention. Mostly we use this sign convention. We have different sign convention, about 3 type of convention, but the most common sign convention is this one. Therefore, it's possible to use the vertical component Vy is equals to V naught sine theta minus Gt for a projectile projected upward. Okay? If it is projected downward, we can use the plus sign. So keep that at the initial component, the horizontal velocity can be determined V naught cos theta. The vertical component can be determined V naught sine theta. But at a given time t, after a certain time t, the horizontal velocity component remains constant since the motion is uniform motion, but the vertical component can be determined using the time t, okay, minus gt. So previously we have found that the vertical component of the initial velocity is 80 meters per second. Suppose what is the velocity of the vertical velocity of this particle after 2 seconds? Let's say that after 2 seconds. So to determine the vertical component of this projected after 2 seconds, Vy is equals to V naught sine theta minus Gt. This is how we put our equation. And the time given is 2 seconds. So when we put this, the initial velocity component, we have already found it to be 80 meters per second. Okay? Minus gravity is 10. We are asked to find the vertical velocity component after 2 seconds. Therefore, you should have to put 2. Therefore, it is 20. 80 minus 20 gives you 60 meters per second. Now look, the vertical component gradually decreases. After 1 second, it becomes 70. After 2 seconds, it becomes 60. After 3 seconds, it becomes 50, and the like, and the like. So at last, it reaches at the maximum height, okay? You have launched it to be 80 meters per second for the example that we have given, 80, 70, and the like. And as it reaches to the vertical, to the maximum height, the vertical component becomes 0, okay? At this point, the vertical component becomes 0 at maximum elevation. But we have said that the horizontal velocity remains constant. Here, initially, we have found it to be 60 meters per second. At point 1, it is 60 meters per second. At point 2, 60 meters per second. Everywhere, it remains constant, the horizontal velocity. But the vertical velocity gradually decreases and it reaches here to be 0. Then gradually it increases, 10 and the like. Okay, it increases and decreases. While it reaches here, it becomes 80 meters per second. While it reaches here, it becomes also 80 meters per second. So this is a projectile motion, and some of the common equations are this one, the initial components, this one, the vertical components after a given time t. It's also possible to discuss about the horizontal and vertical displacement. So far we have tried to discuss about the time interval, the velocity components, the horizontal and the vertical components at time t. Now, how do we determine the displacement, the horizontal and the vertical displacement? We know that the displacement equation is displacement s is equals to velocity initial t plus half at squared. This is the general equations that we use for uniform or uniformly accelerated motion. And we should have to decompose this displacement into horizontal and vertical. For horizontal, we use x, okay? We use x. And for vertical, we use y or h sometimes. Therefore, the horizontal displacement can be rewritten as, instead of s, we use x. Instead of velocity initial, along its horizontal, v naught xt, plus half, the acceleration should be horizontal ax squared. But we have said that the horizontal acceleration is 0 for projectile motion. So this can be 0. This one is 0. Therefore, the horizontal displacement can be given as x is equals to v original x plus t. And we know that the initial velocity component can be given as v naught cosine of theta. Okay, v naught cosine of theta times the time t. This is how we determine the horizontal displacement. Okay. Whereas to determine the vertical displacement, we know that this is the general equation. Instead of using s, we can use y or h. Okay, let's use y. Then the velocity v naught should be the vertical component v naught yt plus half times acceleration along yt. But the acceleration along y is a gravity, so we use g. And the velocity v naught sine theta, the vertical component, the initial velocity component is v naught sine t. So we use plus or minus. We have said that for upward minus, for downward you can use plus. So this is how we determine the velocity component, the displacement vertical component. So y is equals to v naught sine theta t minus half gt squared. This is true for the case that we have. Previously, we have launched vertically upward at an angle of 53 degrees. Suppose, what is the distance, the horizontal and the vertical displacement at time t 2 seconds? If we are asked to find the displacement at time t 2 seconds, we know that x is equals to v naught cos theta. We have already determined it to be 60. From our previous example, it is 60 meter per second. Here we have a time variable. Therefore, if you are asked to find the displacement of that projectile object after 2 seconds, you should have to use 2 seconds. After 3 seconds, you should have to use 3, whatever the time is given. So in this case, the horizontal displacement is 120 meter. 120 meter. How about the vertical elevation of that projectile? Therefore, here we have the initial velocity component to be 80 meter per second. Okay? And you should have to put time t 2 seconds. We have to use 2 minus 1 over 2. Gravity is already 10 for calculation. And the time is 2 seconds squared. Okay. Therefore, this gives us 160. And this gives us 40. You can eliminate 2 squared 4. And here 20. Therefore, when you subtract these two, this gives us 140 meter. The vertical elevation of the projectile becomes 140 meter, and the horizontal projection or the horizontal component is 120 meter. Let's see our projectile here. Suppose after time 2 seconds, it might reach here. Okay, the horizontal displacement x is 120 meter, and the vertical elevation becomes 140 meter. So this is possible to determine the horizontal and the vertical projection. And at maximum height, this is the maximum possible vertical height, it's possible to find the time intervals. Okay? At point 2 means at the maximum possible elevation, it's possible to use the time interval. While the projectile reaches at maximum height, meaning as it reaches here, it took half of the flight. Okay, the time it took is half of the total time flight. Suppose the total time flight is 20 seconds. If it is 20 seconds, it took 10 seconds to reach its maximum height, and the other 10 seconds to reach backward. Therefore, keeping this in your mind, the time it took it reached to the vertical height can be determined using Vy, the vertical component, V naught sine theta since it is projected upward, minus gt. So half-time flight can be determined using this equation. And the vertical, at its maximum height, the vertical velocity is 0. We have said that it is 80 at this moment. For every second, it decreases and decreases. While it reaches its maximum height, the vertical velocity component is 0. So we can substitute here 0 and find an equation. Okay? Here, it's possible to find half-time flight. Half-time flight, because that we have v naught sine theta minus gt, but the vertical velocity component is 0. So v naught sine theta minus g, the time interval, we can call it to be a half-time flight. Half-time flight, so we can have this equation. This is the equation used to determine half-time flight. Half-time flight. And to find the total time flight, for the total projection of the projectile, you can double this time. The total time flight becomes twice of the half-time flight. Okay, half-time flight. It's possible to find that. So substituting this time t on the vertical velocity, the vertical displacement component, you can determine the maximum height. So v naught sine theta times th minus half times gt squared is the way we are trying to determine the vertical component or the vertical height. But instead of time t, we can use half-time flight. If you are trying to substitute here and here, you can find this equation. And this equation is very helpful to determine the maximum possible height for a projectile. So the initial velocity component squared sine 2 theta, sine squared theta, or sine theta squared are all the same over gravity g. Okay, here h maximum can be given as v naught squared sine squared theta. Sine squared theta over gravity g. This is, here we have such an equation, so it's possible to find the maximum possible height. Here it's also possible to determine the maximum horizontal projection. Okay, the maximum possible horizontal projection. To determine this maximum horizontal projection, here, sorry, you do have 2, okay? When you subtract these 2, we can have 2. So v naught squared sine squared theta over 2g is the maximum height. This is how we determine. Now, to find the maximum horizontal projection, the maximum horizontal projection is sometimes called range. So to find that, we should have to use the maximum possible time. As the projectile reaches to the maximum horizontal projection, meaning at half-time flight it reaches to the maximum height, but at the total time flight it reaches to the maximum horizontal projection, and this maximum horizontal projection is called range. That's why we use r. So how do you determine the maximum possible horizontal projection? We know that x is generally given as v naught cosine of theta times t. Here, look, if we use time t to be the total time flight, if you are substituting the total time flight, which is twice of half-time flight, it's possible to find the possible maximum displacement or the range. So maximum horizontal displacement is determined at time t is twice of half of the time flight, t half. Therefore, let's substitute the half-time flight, doubling it, or twice the half-time flight. Let's see here. Here, the half-time flight is given to be v naught sine theta over g. But when you multiply it by 2, you can find it to be the total time flight. Instead of time t, you can substitute this one, it's twice of v naught sine theta over g, so that it's possible to find x. And the x maximum, or we call it to be range, r is equals to v naught squared sine to theta over g. Look here, it says sine to theta. From your trigonometric concept, sine to theta means twice of sine theta cos theta. This should be the way. Sine to theta doesn't mean, okay, doesn't mean twice of sine theta. It is not the same as that of this. It is not the same as twice of sine theta. These are not equal. So whenever you are trying to calculate, note that sine to theta means twice of sine theta and cos theta. Cos theta. Therefore, it's possible to determine the horizontal maximum horizontal component or range. It's possible to determine the vertical component, h maximum. It's possible to determine the velocity component at different locations. So these are the most important points. So far we have tried to see about one-dimensional motion. We have seen about defined motion, and we have tried also to classify different types of motion depending on acceleration. We have also seen about the projectile motion or motion in two dimension. Since one of the two-dimensional motion is projectile motion, we have seen about projectile motion so far. So this is all that I've got for today. Next time we'll try to see about circular motion. Thank you. Goodbye.